Now, the latest development from Google that it describes as a state-of-the-art quantum computer chip.
Voyager 1 has traveled farther than any human-made object in history, hurtling through the uncharted depths of interstellar space. Packed with decades of cosmic data and humanity's golden record, it continues to send signals back to Earth from over 14 billion miles away. But recently, NASA's AI quantum chip analyzed its latest transmission and uncovered something unexpected. Hidden within the familiar patterns of data lies a cryptic message no one saw coming. Could this be an interstellar anomaly or something else? What secrets is Voyager 1 keeping from us? The origins of Voyager 1. Voyager 1 launched on September 5, 1977, as part of NASA's ambitious plan to explore the outer solar system in unprecedented detail. Most people also recall its twin, Voyager 2, which actually left Earth 2 weeks earlier but was placed on a different trajectory. The idea for the Voyager program grew out of earlier successes, including the Mariner missions to Venus and Mars, and the Pioneer probes that traveled beyond the asteroid belt to Jupiter. Yet Voyager was designed to push much farther, gathering closer observations of the giant planets, and then venturing into the deeper reaches of space. In the early 1970s, NASA recognized a rare alignment of the outer planets that would let a single spacecraft visit multiple giants by using gravitational assists. This arrangement, which only arises about once every 176 years, allowed a series of slingshot maneuvers past Jupiter, Saturn, Uranus, and Neptune for Voyager 2. Voyager 1, however, would focus primarily on Jupiter and Saturn, then speed away from the ecliptic plane after its Saturn encounter. From a technological standpoint, the project built on lessons from Pioneer 10 and Pioneer 11, which first braved Jupiter's hazardous radiation belts. Scientists and engineers learned about the potential dangers, including the intense charged particle environment around gas giants. These experiences shaped Voyager 1's protective design. Assembled at the Jet Propulsion Laboratory, JPL, in Pasadena, California, the spacecraft included robust shielding, backup systems, and advanced imaging and sensing instruments. Funding and time constraints pressed the team to finalize Voyager 1's design rapidly. Each instrument had to fit strict mass, volume, and power budgets. NASA also prepared to gather as much data as possible in one dramatic pass of Jupiter, followed by another pass of Saturn. The pace was intense, but the payoff would include the best images yet of these giant worlds and their many moons. Originally, mission planners expected Voyager 1 to work for just a few years, enough to complete the Jupiter and Saturn flybys. However, as we now know, the spacecraft's longevity surprised nearly everyone, eventually enabling it to become an explorer of the farthest regions of our solar system. Designing a spacecraft for the outer solar system. Voyager 1's design was heavily shaped by the need to survive extreme radiation, low light conditions, and long communication delays. Unlike spacecraft operating closer to the Sun, Voyager 1 could not use solar panels for power. Instead, it was equipped with 3 radioisotope thermoelectric generators, RTGs, each containing plutonium-238. The slow, predictable decay of plutonium produces heat, which is converted into electricity. Engineers calculated that these RTGs would supply the craft for multiple years, enough to complete the Jupiter and Saturn encounters. They also hoped, perhaps optimistically, that the remaining power might let it remain active even longer. Inside the spacecraft's central bus, key subsystems manage power distribution, navigation, communications, and data handling. The high-gain antenna, measuring about 3.7 meters across, points back to Earth to transmit everything collected by the onboard instruments. Because the transmitter had to operate with limited wattage, NASA needed extremely sensitive receivers on Earth to pick up Voyager 1's faint signals. Early on, the data rate could be measured in kilobits per second near Jupiter. Later, as the craft moved farther away, it dropped substantially. Voyager 1 carries a suite of instruments for in-depth studies. Some of the most notable are the Imaging Science System, 2 cameras, wide-angle and narrow-angle, the plasma spectrometer, cosmic ray detector, magnetometer, and a plasma wave subsystem. Each needed to be hardened, at least to an extent, against the harsh radiation of the outer solar system. For instance, Jupiter bathes its surroundings in charged particles trapped by its monstrous magnetosphere. Keeping these instruments from interfering with each other required careful placement. The magnetometer, for example, sits on a separate boom away from the spacecraft body to limit magnetic disturbances from onboard electronics. Cameras and other sensors reside on a scan platform that can pivot. Engineers also included tape recorders to store data temporarily when real-time transmission to Earth was not possible. Memory space was modest, on the order of tens of kilobytes, so data management was extremely strategic. Radiation damage was a critical concern. The spacecraft's 1970s-era integrated circuits were relatively large-scale by modern standards, which in some ways provided better resilience. Nonetheless, NASA had to shield vulnerable components, use error correction codes, and design robust fault-handling software. Over time, the project included redundant hardware. If a primary module failed, a backup unit could take over, at least in theory. This feature would later become crucial for dealing with glitches beyond Saturn. The Grand Tour of the Outer Planets. Voyager 1's journey to Jupiter began shortly after launch, capitalizing on the planet's powerful gravity to fling the spacecraft onward towards Saturn at high speed. In early 1979, it reached the Jovian system. For many, its close-up photos were a revelation. Jupiter's swirling cloud layers, the massive Great Red Spot, and the newly discovered volcanic activity on the moon, Io. Until then, no one had seen active volcanoes beyond Earth. Having near real-time images of Io's eruptions and Europa's mysterious icy surface spurred scientists to rethink how dynamic these moons could be. Ganymede and Callisto also showed varied terrain, from dark scars to bright ridges. The spacecraft's instruments measured Jupiter's intense magnetic field, discovering that it stretched even farther into space than previously believed. High-energy particle radiation encountered near the planet challenged Voyager 1's systems, but the spacecraft survived, confirming that NASA's precautions were effective. This success alone would have made the mission worth it, but the main part of the mission, Saturn, was still ahead. In late 1980, Voyager 1 arrived at Saturn. The images of Saturn's rings were breathtaking, revealing ringlets and braided features that hinted at complex gravitational interactions. The spacecraft also studied Titan, Saturn's biggest moon, which turned out to have a thick, nitrogen-based atmosphere even denser than Earth's. That particular finding set the stage for future missions like Cassini-Huygens, which eventually landed a probe on Titan's surface in 2005. Voyager 1 thus laid the groundwork for an entire generation of outer planet exploration. Among the most iconic moments was the spacecraft's close pass by Saturn's ring. Scientists identified gaps like the Cassini division and unexpected radial spokes that defied older theories. The pictures were widely published, sparking global fascination with ring phenomena. Once the flyby concluded, Voyager 1's trajectory took it high above the plane of the solar system. This effectively ended its grand tour, leaving Voyager 2 to continue on to Uranus and Neptune. NASA recognized that keeping Voyager 1 alive for deep space observations might yield groundbreaking data on the solar system's outer boundary. So from November 1980 onward, the spacecraft was directed into an open-ended extended mission phase, occasionally dubbed the Voyager Interstellar Mission, crossing into interstellar space. After Saturn, the main tour was over, and Voyager 1 soared on a path that would eventually take it outside the heliosphere. The heliosphere is like a vast bubble inflated by the sun's solar wind, a stream of charged particles escaping the sun at high speed. Where that wind meets the interstellar medium is called the heliopause, a zone that defines the boundary between our solar bubble and true interstellar space. For years, scientists argued about how far away the heliopause might be and what crossing it would look like. By mid-2000s, Voyager 1 measured changes in particle flux, indicating it was approaching the termination shock, where the solar wind abruptly slows. Then, in August 2012, NASA announced that data strongly suggested the spacecraft had crossed into the interstellar medium itself. The cosmic ray detectors observed an increase in galactic cosmic rays, particles from distant astrophysical sources, and a drop in solar particle. Plasma wave instruments also recorded frequencies hinting at a denser plasma environment than inside the heliosphere. Though the crossing wasn't a sharp, instant boundary, the differences in the data sets were compelling. Voyager 1 had gone where no human-made object had gone before. Scientists were jubilant, calling it a new phase of discovery. Although the spacecraft remained physically in our galaxy, it was the first time we studied the density, temperature, and composition of interstellar plasma up close. Occasional shock waves still emanate from the Sun and reach this region, but the environment is mostly defined by factors beyond direct solar influence. This milestone signaled a shift in how NASA viewed Voyager 1. Now the spacecraft's primary job was to sample cosmic rays, measure interstellar magnetic fields, and note any transitions. The data trickled in from an immense distance, taking over a day to traverse space at light speed. Despite the slow pace, each new reading was precious, telling us how stars shape the space between them. Over a century from now, Voyager 1 will continue drifting through the Milky Way, an inert observer carrying a faint imprint of Earth. The unexpected telemetry issue. In March of a recent year, NASA noticed that Voyager 1's transmitted engineering data went from normal to bizarrely corrupted. Telemetry data, which typically includes information about orientation, power usage, and subsystem status, showed jumbled bits akin to white noise. Engineers, used to occasional anomalies on a spacecraft launched in 1977, initially suspected hardware degradation. Over decades, cosmic radiation can accumulate and electronics can degrade. However, repeated attempts to fix it using standard approaches, such as resetting memory or switching to backup modes, failed to clear up the unusual signal. Conventional decoding processes treated the corrupted data as random, yet NASA observed that the patterns became more frequent instead of disappearing, which was atypical for a mere hardware dying scenario. The engineering team began to suspect that the onboard flight data subsystem (FDS) or a related memory chip might have developed a systematic fault. Around this time, younger researchers at JPL proposed feeding the seemingly random signals into specialized quantum-based pattern recognition software, partially inspired by prior experiments in analyzing cosmic background data. This approach was new for NASA's real-time mission data. The idea was that quantum computing could uncover subtle correlations or structures invisible to classical algorithms. Even if it only helped diagnose a hardware glitch, NASA was open to any method that might solve the puzzle. To everyone's surprise, initial quantum analysis indicated the data had structured segments that repeated. This was unexpected because a failing chip typically produces raw noise or incomplete packets, not repeated shapes or sequences. NASA was still cautious. Software illusions can arise if quantum algorithms project patterns onto random input, but the lead engineering teams realized they needed to keep investigating. In the meantime, NASA alerted the public to unusual telemetry issues, stating the spacecraft otherwise remained healthy. As the odd signals persisted, speculation grew about whether some deeper cause existed or if it was simply an artifact of advanced data mining. NASA's troubleshooting efforts. When NASA confronts an anomaly on an aging spacecraft billions of miles away, They follow strict diagnostic steps. Each uplinked command takes over 20 hours to reach Voyager 1, and the response requires another 20 hours, so real-time diagnostics are impossible. The mission team typically starts with small tests that isolate memory blocks, reroute subsystem data, or switch to hardware backups. In this case, the prime suspect was the flight data subsystem or its memory addresses. Engineers discovered that the standard memory location where housekeeping data was written might have a failing region. They tried commanding the spacecraft to use a different block for storing telemetry. Yet even after partial success, the signals persisted with bursts of random content. Nonetheless, reconfiguring the memory did get them partial fixes. NASA soon recovered some normal fields, orientation angles, temperature readings, and voltage levels that restored at least basic insight into Voyager 1's health. Then the quantum scientists, working in parallel, flagged residual pockets of data that still displayed non-random repetition. Around this time, NASA implemented more isolation tests, examining raw waveforms from the Deep Space Network before applying standard decoding. They also cross-checked signals from different DSN sites to rule out local station interference. All sites confirmed that odd patterns came from the spacecraft's actual transmission, not an Earth-based glitch. By the end of that spring, NASA commented publicly that they had partly resolved the telemetry problem but were investigating anomalies in the data stream. The official line was that hardware deterioration was the most likely culprit, while the quantum analysis was seen as an experimental method for advanced troubleshooting. NASA's classical engineers wanted more definitive evidence before they declared anything beyond a memory glitch. The role of the Flight Data Subsystem. The Flight Data Subsystem, FDS, is central to Voyager 1's operation. It packages data from scientists' instruments and from housekeeping sensors into a format that NASA can decode. It applies error correction codes, organizes telemetry frames, and sends them to the main transmitter. If something inside the FDS fails or miswrites the data, ground control sees unreadable or meaningless signals. This subsystem was designed in the 1970s using integrated circuits far less powerful than modern chips, but it had a strong track record of reliability for decades. Originally, the FDS stored instructions in read-only memory. Additional work areas existed for ephemeral data. Over time, NASA uploaded minor software patches during planetary flyby, but the core architecture never changed. If speculation arises about an unintentional emergent pattern or random glitch, it typically points to failing hardware or cosmic ray impacts damaging memory bits. For a malfunction to produce stable, repeated sequences of data is unusual. Standard malfunctions give partial frames, missing bits, or random fluctuations. Because the FDS directly interfaces with the transmitter, any external phenomenon must pass through it if it wants to embed signals in the downlink. Some folks suggest that advanced pattern recognition might be misreading typical interference from the DSN or the interstellar environment, but NASA's cross-verification indicated the raw radio signals were indeed carrying the anomaly. Meanwhile, the FDS itself did show signs of wear, implying that NASA has reason to believe the anomalies are partly a hardware matter. Troubleshooting the FDS includes rerouting memory writes and using backup addresses. NASA also has the option to switch wholly to a backup flight data system if needed, but that is a hazardous step for such an old craft. The backup hardware might have dormant faults. For now, the main approach is to keep the partially functional FDS running, guided by software patches that sidestep the worst memory blocks. In short, the FDS remains the spacecraft's bottleneck for data flow, so any persistent glitch must be addressed at that level. The Golden Record. One of Voyager 1's most famous elements is the Golden Record attached to its exterior, a gold-plated copper disc curated by a team led by Carl Sagan. It contains sounds and images selected to portray a snapshot of life on Earth at the time of launch. These include musical pieces, from Bach to Chuck Berry, greetings in multiple languages, natural sounds like wind, thunder, and bird calls, and diagrams that could guide a hypothetical finder on how to play it. There's also scientific and mathematical information illustrating Earth's location and the fundamentals of human knowledge as understood in the 1970s. The golden record was intended as a message in a bottle for whatever might eventually come across Voyager 1. NASA never designed the probe to broadcast that record's contents in its radio transmissions. It simply bolted onto the craft, yet the record became a cultural icon, symbolizing the mission's spirit of exploration. Over decades, the presence of the golden record shaped public perception. People often see Voyager 1 not just as a scientific mission, but as Earth's ambassador in the cosmic ocean. In the context of the recent telemetry anomaly, the golden record garnered fresh attention. Some outside observers speculated, without evidence, that the record's references might be showing up in the corrupted data. NASA has stated that there is no direct link between the record's analog grooves and the spacecraft's digital telemetry. The record is a physical artifact, separate from the FDS or any communications software. That said, the record's existence continues to drive popular curiosity about whether Voyager 1 could be answered by something out there. NASA's official stance is that while the golden record is an inspiring gesture, the new anomalies are more likely due to ordinary technical factors, and any discussion of a direct reply tying the record to telemetry remains unproven. Transmission from beyond 15 billion miles. As of the most recent data, Voyager 1 is over 15 billion miles from Earth, a figure that continues to climb daily. This immense distance makes communication extraordinarily difficult. Signal strength falls off with the square of distance, so NASA relies on its largest deep space network, DSN dishes, some up to 70 meters in diameter, to capture the spacecraft's faint radio emissions. Advanced amplifiers, digital signal processing, and error correction codes help reconstruct readable frames. Because it takes more than 20 hours for a signal to travel one way, any real-time fix is impossible. Everything happens in slow motion. The mission team sends a command and waits nearly 2 days to see if it helped. Even more challenging, the craft's diminishing power supply forces NASA to shut off some instruments or heaters periodically. That means data rates and operational modes must be carefully rationed. Starting in March, the persistent garbled portion of Voyager 1's telemetry drew increased attention. The question arose, could something else be piggybacking on the transmission? Again, NASA found no direct evidence beyond the odd patterns that advanced analysis flagged, but the intricacy of the signals, if real, surprised many. Over time, NASA tried alternative receiving modes, even using backup communication channels. The anomalies remained intact across all channels, indicating they were not a DSN artifact. Interstellar medium observations. While the anomaly captures headlines, Voyager 1 continues to deliver vital readings about the interstellar medium. Outside the heliopause, the spacecraft's detectors measure how cosmic rays from distant supernovae traverse the galaxy. Researchers compare these readings with Voyager 2's data to see if the boundary region is symmetric or if conditions differ depending on the direction of travel. The cosmic ray subsystem observes differences in particle spectra, shining light on how magnetized plasma shapes cosmic ray paths. The magnetometer readings confirm that interstellar space is not uniform. Subtle fluctuations in the magnetic field point to the sun's outbursts traveling outward with diminishing strength. Periodic shock waves can still pass the spacecraft, compressing local plasma. By spotting these waves, scientists see how far the sun's influence extends. Plasma wave instruments record faint whistles and hums that can be played back as audio for the public, dramatizing what otherwise would be intangible data about charged particles. Dust measurements are another key aspect. Voyager 1 occasionally feels impacts from small grains of interstellar dust. Each impact sends a spike through the spacecraft's sensors, revealing dust density in that vast emptiness. Studying dust composition is central to understanding how material recycles between stars, fueling new star systems. Because dust forms part of the raw ingredients for planets, these observations tie into bigger questions about how planetary systems like ours might form across the galaxy. Communication challenges. Communication with Voyager 1 is an ongoing triumph of engineering. Collecting bits of data from around 15 billion miles away calls for enormous Earth-based antennas, advanced digital filters, and robust error correction. If the craft drifts even slightly, or if a subsystem glitch occurs, the data can degrade further, as we've seen with the recent telemetry anomalies. NASA's slow but methodical approach, sending commands, waiting days to see results, is the only way to maintain a stable link. The challenge also highlights bigger questions about how we observe the universe. NASA's quantum-based experiment with the Majorana 1 chip indicates that future missions might rely on advanced pattern recognition from day one. If subtle hidden signals or complex anomalies occur, quantum computers might tease them out. Of course, applying new technology requires rigorous verification. NASA keeps an official stance that any unusual patterns in Voyager 1's data need thorough cross-checking with classical methods. However, more labs worldwide are rechecking raw transmissions for anomalies once considered random noise. NASA's official position is that the mission end date will come whenever the power can no longer support the transmitter. Until then, they will keep working to glean fresh insights from every byte of data. The spacecraft's achievements underscore perseverance in both engineering and science. Voyager 1 has written new chapters in planetary exploration. It has become the pathfinder for studying interstellar space firsthand, and it keeps offering hope that even from billions of miles away, we can learn more about ourselves and our corner of the galaxy. When it finally goes silent, future historians may look back on these final years of transmissions, messy glitches and all, as a fitting close to one of humanity's grandest voyages, and a reminder of what dedication and clever problem-solving can accomplish over the span of generations. Thanks for watching another episode. While you are still here, make sure to click the video on your screen for more quality content.